Hi, my name is Chris, and I've been asked to talk about a really interesting subject, and that's whether life exists outside of Earth and where we would find it. First, I want to break this subject down into two parts. The first part being, where do we find life outside of Earth in the solar system? And the second part being, where do we find life outside of Earth in general? So, if we're talking about the solar system, we have a couple good options. One of the options is Mars. Mars has been popular. Mars has been popularized in fiction, and it's been popularized in all the recent missions that we've taken there. Now, there's a reason why Mars is so popular. Mars is very similar to Earth as being a rocky planet. It's not too far from the sun, and we think that the conditions of Mars used to be just right for life to develop. So it's possible that life could still exist to this day. Now, the problem with Mars is that Mars has a very thin atmosphere compared to Earth. The Martian atmosphere is roughly 6 millibars, which is 6/1000ths that of Earth's. Now, what this thin atmosphere does to Mars is that it creates a really low atmospheric pressure. That, coupled with the low temperatures on Mars, sometimes at the highest reaching probably the lowest of Antarctica. Um, that coupled with the pressure leads to liquid water being unstable at the surface. Now, this is a problem because we know that liquid water is a medium for life as we know it here on Earth. Water is our universal solvent. Water causes all biochemistry of ours to thrive. We're also carbon-based organisms. And with all these carbon-based organic molecules, water is the perfect solvent for that to take place in. So if we were to evaluate the possibility of life on other planets, there's only one route that we can go right now with any certainty, and that's to evaluate any life that's similar to life on Earth, or life as we know it, such as carbon-based life and life that requires water as a solvent. So when astrobiologists go to figure out where they would look for planets that have life, they typically look for planets that are close to their star, but not too close. So you want to find them in a zone around their star where it's not too hot and it's not too cold. You want liquid water to be able to exist on the surface for long periods of time. And so you also need enough atmospheric pressure. This means that this planet needs to be massive enough to hold on to an atmosphere for billions of years. This is a problem that Mars has had. We know that Mars, from these rovers that have gone up, including Curiosity, to study the early conditions on Mars, we know that Mars used to have flowing rivers, flowing lakes, flowing oceans. This was a period of time about 3.5 to 4 billion years ago. And during this time, Earth also had liquid water on the surface. But Earth also had life on the surface at this time. So is it possible that Mars, because its conditions were not so distinct from Earth, could have also had life at the time? So there's actually a mission called ExoMars that's being planned for 2020 that will be the first life detection mission in decades. The purpose of this mission is to examine whether Mars preserves fossils of life, of early life. Now, when we're talking about fossils of life, we're not talking about fossils of life like dinosaurs. We would never expect to find dinosaurs on Mars. We're talking about early life, such as single-celled bacterial or archaeal type life. The second term that I mentioned, archaeal, that's a type of organism that is very similar to bacteria. And in recent years, we've thought about them being related to bacteria, but in fact, they're actually more closely related to us. Like bacteria, they're single-celled organisms. They differ in some aspects in the types of shapes that they come in and the proteins that are found in their cell membranes. Because what this allows them to do is it allows some archaeans to survive under extreme conditions. These would be conditions like around hydrothermal vents in high temperature waters, sometimes surpassing boiling temperatures. And keep in mind that they're surpassing boiling temperatures. It's because the water is down at significant depth that the water is able to stay a liquid instead of gas, is able to stay superheated instead of boiling. the pressure is so high, and remember there's a relationship between pressure and temperature, that if your pressure is really high, you can raise the boiling point. So you have organisms like the archaeans that live around the deep sea vents. You have organisms that can survive extremely acidic, extremely basic environments. And these are the type of organisms that we're looking for. These are the type of organisms that we'd find in extreme conditions like those that we'd find on Mars. So the plan of ExoMars isn't to search for extant or living life, it's to search for extinct life in the form of fossils. And we have numerous examples of microbial fossils on Earth. And so we have an idea, rough idea, of what sort of structures to look for and what differentiates these structures from natural geological structures. Now, moving on from Mars, the next area I'm going to touch on is the icy moons. One of the icy moons is the second moon of Jupiter. It's called Europa. Europa has recently been popularized in fiction, and we think that perhaps it's even a better place to look for life than Mars. Europa is an icy moon. It's got a layer of ice roughly 16 kilometers thick on top of what appears to be a liquid water ocean underneath. We know that it's a liquid water ocean based on density measurements of Europa and the degree of heating it receives from Jupiter. Given that it has this liquid water ocean, an ocean that may be even larger than all the reservoirs of water on Earth, it's possible that life could have developed deep in the ocean, somewhere around the hydrothermal vents of Europa. We know that life, or it's actually a hypothesis that life could have developed around these hydrothermal vents on Earth. It's very much possible that life could have developed in the same way on Europa. Either way, Europa's been around for just as long as Earth has, and it's had just as long to evolve. And we know that the key ingredients for life are found everywhere. These key ingredients for life are in the form of simple organic molecules such as amino acids. The only thing that we're missing in the picture of how life originated is how amino acids then link together to form proteins, and how these proteins assemble together to form units like cells, like organelles, and later on the cells, and to organize tissues. So we know that the essential ingredients for life are everywhere. We found them on asteroids, we found them in comets, and we found that there are natural ways in which amino acids can form from even inorganic compounds. On asteroids and comets, we found that how they form is you can have these inorganic molecules such as methane, such as ammonia, such as water vapor, and subject them to some highly energetic process, such as ionizing rays from cosmic radiation, or from, if you're testing something in the lab. Actually, there was an experiment that was done in 1953 by Miller and Urey. In this experiment, they demonstrated that you could take inorganic compounds and subject them to some sort of energizing reaction. In their case, they subjected it to a spark of electricity. Once it's been subjected to the spark of electricity, what happens is this medium full of these organic molecules is heated up and condensed. Once it's condensed, it forms into a solution where we see this formation of inorganic molecules into simple organic molecules such as amino acids. And the same process happens out in space on asteroids and comets. So the essential ingredients, including all the elements, carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, these 6 essential ingredients are the ingredients that are essential to life as we know it, and they're found everywhere. Mix these ingredients and liquid water, and with some luck, you have life like we find here on Earth. So going back to Europa, Europa is a great opportunity. Has a lot of potential for finding life because we have a deep ocean with who knows what is developed under that ocean. Only problem would be that any future probe that we send there would have the task of drilling through kilometers deep of ice and having to send a submarine down into an ocean that's much deeper than any ocean on Earth. The next possible location for life, I would say, is Enceladus. Enceladus is also an icy moon, and this is an icy moon of Saturn. Enceladus is much smaller than Europa and has a much smaller ocean, but from probes that have gone to visit Saturn, such as Cassini, we've found that Enceladus actually emits these huge geysers, these plumes of liquid water that give us an idea of what the ocean's composition is like. And it tells us that it's a very salty ocean that is a very good abode for life. So as with Europa, there's a possibility that life could have evolved deep in the oceans of Enceladus in some small pockets. Another possibility for life is another one of Saturn's moons, and this moon is Titan. Titan is the second largest moon in the solar system, and it's the only moon in the solar system that has an atmosphere, has a thick atmosphere. In fact, its atmosphere is so thick, it's 1.5 times the thickness of Earth's atmosphere. Titan has landscapes that look just like Earth. From the Huygens probe that was sent to Titan, we know what its surface looks like. We know that it has mountains, we know that it has lakes, rivers, and oceans. However, these are not mountains made of rock. These are mountains made of ice. And these are not oceans, rivers, and lakes made of water, but there's oceans, rivers, and lakes made of hydrocarbons such as ethane and methane. The temperatures on Titan are very unforgiving. They're cold, extremely cold, cold enough that these compounds would exist as a liquid. If any life does exist there, it would indeed be alien to life on Earth. The biochemistry would be completely distinct from Earth's, and really we have no idea where to start if we were to look for life. The only thing that we would look for is signatures for life that we can look for in the absence of any knowledge of biochemistry is if we find excess of certain compounds that we don't know of forming from any sort of natural processes. Of course, this itself is not a smoking gun, because just because we don't know how certain compounds are formed doesn't mean that these can automatically be attributed to a product of life. So finding life on Titan would be tricky, and any life that we find would be very alien to us using biochemistry. It's probably still carbon-based, but would rely on a completely different universal solvent rather than water, possibly ethane or methane as its solvent. So expanding outside of our solar system, what I was talking about in the solar system was the possibility of finding life, period. This doesn't mean that we're going to find any complex life. We might find bacterial or single-celled life. If we wanted to find life that was more complex, I think more opportunity exists on planets that are surrounding other stars. Unfortunately, this is so out of reach that we probably won't be able to confirm a lot of these discoveries for decades or maybe even centuries. However, we can get started. Kepler, a space telescope that was sent up years ago to study a small region of the Milky Way galaxy, has been essential in the hunt for exoplanets. Now, ever since 1995, when the first official exoplanet was discovered, this exoplanet was 51 Pegasi b. It was a planet discovered around a pulsar. This is the first time a planet was discovered around another star, and in 20 years, we've discovered over 3,000 exoplanets orbiting other stars. This is a great fact to know, because those who were born in the 1980s were born in a time where we didn't know of any other planets other than those in our solar system, and every other planet that has been discovered to this date has been discovered since they've been alive. Kepler has given us a view of what sort of planets are out there. Up until recently, because of early methods that were used to discover these planets, including the method that was used to discover 51 Pegasi b, these methods were biased toward discovering very large, massive planets that were orbiting closely to their stars. There's still a bit of this bias existent in the methods that we use now. The method that was used back then is called the radial velocity method. It's still used now to discover those types of planets. What this does is it's a method that relies on the close relationship between the gravitational relationship between a massive planet and that of its star. If a planet is more massive, then it's going to cause a slightly greater disturbance on its star. Whereas if you take a planet the mass of the Earth, it's barely going to influence a star the mass of the Sun. You need something much more massive to show a significant movement that be detectable in the radial velocity method. So as you can imagine, most of these early discoveries of exoplanets were planets that were discovered far too massive and far too close to their suns, their stars, to be eligible candidates for life. Now, Kepler and a lot of more recent space telescopes are using a method called the transit method to discover smaller planets. The transit method is a method that relies on a star and its whole planetary system being within our plane of view. So you have to have a planet that crosses in front of the star to our point of reference. What this does is the method looks at the brightness curve of a star over a period of time, and it detects any dips in brightness that appear to be periodical. Let's say if you have the same exact dip in brightness every 3 or 4 years, you can be sure that there's something of consistent size that's orbiting around that star every 3 to 4 years. And so we use this method to determine how far away the planet is orbiting from its star, roughly its size, its radius, and its minimum mass as well. With its minimum mass, we can get an idea of what type of planet it is, because there seem to be certain regimes of planets. We go from small rocky planets to liquid planets that are about 10 times the mass of Earth, to gaseous planets that are much more massive than Earth, such as we find in our solar system, like Saturn, which is 95 times the mass of Earth, and Jupiter, which is 315 times the mass of Earth. So it's not really these gas planets that we're looking for when we look for life. It's the rocky planets that we look for when we look for life. So as you can imagine, looking for such a small planet, a small rocky planet that's passing in front of a star, is akin to looking at a lighthouse and trying to detect a moth passing in front of the lighthouse from miles and miles away. Except we're looking at a star that is light years away and looking for something that causes a dip in brightness of less than 1%. How do you detect something like that? You take a lot of observation. And that's the goal of Kepler. That has been the goal of Kepler up until it's been out of commission. So during the time that it's been up, it's discovered some 3,000 planets or so. And it's given us a better view of the distribution of the types of planets in our galaxy. Now, we've known for decades roughly how many stars are in our galaxy, and this number is about 200 billion. It isn't until recently that we've had an idea of how many stars actually have planetary systems, and how many of these planetary systems have Earth-like planets. Kepler has given us an answer, and that number seems to be roughly 40 to 50 billion Earth-like planets in our Milky Way galaxy. Now, go back to earlier where I talked about how the ingredients for life were the simple 6 elements: carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, and their compounds, such as amino acids and lipids and carbohydrates, and also the prevalence of liquid water on the surface. So right now we look for rocky planets that are within the habitable zone of their stars, within the zone of their stars where it's not too hot and it's not too cold for liquid water to occur on the surface, and where there would be the presence of organics. So, given the number 40 to 50 billion Earth-like planets in our Milky Way galaxy alone, even if the odds of life arising from those simple organic compounds in the existence of water, even if the odds were 1 in a million, if we had 50 billion planets, that means there's 50,000 times. That's happened 50,000 times in the galaxy already. That gives us an idea of what our odds are when looking for life on other planets. Of course, there's other factors to take into account, but also keep in mind that our galaxy is one of trillions of galaxies in the observable universe. Thank you.
I think it's pretty much like 2 minutes, something like that.
I tried to estimate 20 minutes.
Yeah. Okay. Yeah. I can only